Okay, the next carboxylic acid derivative we have are esters. So we know an ester is a carboxylic acid where the OH has been replaced by an alkoxy group. And one way to make esters is through an SN2 reaction. So if we have an alkyl halide that is effectively the substrate, by using sodium hydroxide we can deprotonate the carboxylic acid, and then this O- becomes a good nucleophile. And so then this acts as a nucleophile, the iodine acts as a leaving group, and we get the ester. Another way to make esters is through Fischer esterification. And this is just an example of nucleophilic acyl substitution under acidic conditions. And in fact, the mechanism example, when we first introduced this type of substitution, was an example of Fischer esterification. In the Fischer esterification, we start with a carboxylic acid and we react it with an alcohol under acidic conditions. And that will give us the ester. Now, we've already seen an example of this mechanism, but let's look at another case. All right, so in these nucleophilic acyl substitution reactions, if we're in acidic conditions, we almost always start with a proton transfer. And that's what happens in this case. So we have the protonated alcohol acting as the proton source. That's followed up by nucleophilic attack. Remember, the two core steps in these nucleophilic acyl substitution reactions are nucleophilic attack and loss of a leaving group that we'll see later. So now the alcohol acts as a nucleophile. When we want the loss of a leaving group, which is going to be one of these OHs, under acidic conditions, OH is not a good leaving group. We can't make OH minus under acidic conditions. So this needs to be protonated. But before I can protonate the alcohol, I have to deprotonate this guy. So I can't put two positive charges near each other in the same molecule for the mechanism to be considered a reasonable mechanism. So first I need to deprotonate this guy, then I can protonate the OH that's going to act as the leaving group. So the alcohol will act as the base and deprotonate this methoxy group. Now that I've deprotonated this methoxy group, I can protonate the OH to make it a good leaving group. So the protonated the protonated alcohol will act as the proton source. Now I have a good leaving group, so the OH can come off. The driving force is the reformation of this carbonyl bond. Then I still have a charge in my molecule, and so to get rid of that, again, the methanol acts as a base to deprotonate this guy and give me the final product. This esterification is an equilibrium process, and we're actually going to see the reverse of Fischer esterification. We're going to see hydrolysis later on in this video. So we can use Le Chatelier's principle to favor the products. So there are a couple ways to do that. We can either use excess methanol by adding excess reagent that will drive it to favor the products, or we can find some way to remove water from the system when we remove a product that will also shift the equilibrium to favor the product side. Okay, so we've already seen two ways to make esters. One is through an SN2 reaction by reacting it with a base and then an alkyl halide. We've seen Fischer esterification by reacting it with an alcohol under acidic conditions. The third way we can make esters is by starting with an acid chloride and reacting that with an alcohol. And we saw this reaction in the acid chlorides video. The pyridine is there to neutralize the HCl that's produced in the course of the reaction. So we've seen three ways that we can make esters. Now we're going to turn our attention to reactions of esters. And the first two reactions that we're going to look at are both hydrolysis. So two different ways of converting the ester back to a carboxylic acid. The first way is through using a base as a catalyst, and this process is called saponification. So if I treat this ester with sodium hydroxide, it will convert it into the carboxylate ion, right? When we're in basic conditions, even if we initially make the carboxylic acid, that's not going to be stable under basic conditions. It's going to be deprotonated to form the carboxylate ion. So the acid workup is necessary to reprotonate that carboxylic ion, or that carboxylate ion, to give us the ester. So if we take a look at that mechanism, this is just another example of the nucleophilic acyl substitution. This time we're in basic conditions. Generally, we need a proton transfer if we're in acidic conditions at the start of the reaction. In basic conditions, that's generally not necessary. And so we can immediately attack our ester with the nucleophile. In this case, it's going to be the hydroxide ion because we're in basic conditions. Then we know the two core steps are nucleophilic attack and loss of a leaving group. In this case, I don't need to protonate this leaving group because we're in basic conditions, so making the RO minus is not a problem. And in fact, I can't protonate this because if I have a positive charge on an oxygen, that can't exist in basic conditions. So there's no proton transfers necessary before we get to the loss of a leaving group. We'll reform the carbonyl double bond. The alkoxy group pops off as the leaving group. Right. Now, we've made the carboxylic acid, but because we're in basic conditions, we've got sodium hydroxide, or now we have this alkoxy ion roaming around, it's going to deprotonate any carboxylic acid that we form. And so we're going to end up with a carboxylate ion. And so if we want to get back to the carboxylic acid, that's where the acid workup comes in. So in a separate step, if we add an acid source, then we can reprotonate that carboxylate ion and generate the carboxylic acid. The next reaction is still hydrolysis. This time we're going to be under acidic conditions, and this is the reverse of the Fischer esterification. Right, with Fischer esterification, we used acidic conditions, and we reacted the carboxylic acid with an alcohol to form our ester, and we said it was an equilibrating process. We can go in both directions. Well, this is the reverse direction. So when we were thinking about Fischer esterification, in order to favor the ester, we used excess methanol, or we removed water from the equation somehow. If we want to go the other way, we would add excess water to the reagent side, or we would want to remove the alcohol somehow. The mechanism is exactly what one would expect for nucleophilic acyl substitution under acidic conditions. In fact, all the steps for Fischer esterification are exactly the same as this process. It's just that in this case, water is the nucleophile instead of the alcohol, and then now the alcohol is the leaving group instead of the water in the Fischer esterification process. But otherwise, the mechanism is identical. Okay, we've seen aminolysis before with acid halides and the acid anhydrides. We can do the same thing with an ester. If we react it with an amine, we can form the amide. Now, in this case, the equilibrium does favor the formation of the products because the amides are less reactive or more stable than the esters. That being said, the synthetic utility is a little bit limited because the process is very slow. It's generally much easier to start with carboxylic acid, make the acid chloride, and then do the aminolysis on the acid chloride rather than on an ester. We also saw reduction reactions when we were looking at the reactions of acid chlorides, and the process is very similar when we have esters. When we react it with lithium aluminum hydride, we get the primary alcohol. Two equivalents of the reducing agent are needed because it's two steps. First, we'll convert it into the aldehyde, then we'll convert it into the alcohol. The mechanism is exactly the same as the mechanism that we saw for the reduction of acid halides with lithium aluminum hydride. And even though we've seen this mechanism before, it may be helpful to look at it again. we start with a nucleophilic attack. So the hydride from the lithium aluminum hydride acts as our nucleophile. We then have the loss of the alkoxy group as a leaving group. Then we have a second nucleophilic attack. Again, the hydride is coming from the lithium aluminum hydride. And we end up with this charged alkoxide ion. And so the final step is a proton transfer to give us the primary alcohol. Now, as we saw with the acid halides, and again with the esters, when we use lithium aluminum hydride as the reducing agent, we can't stop at the aldehyde. This is such a powerful reducing agent that we all go all the way to the primary alcohol. An alternate reducing agent, so the book writes it as DIBAH. I've also seen it written as DIBALH. And so sometimes I've seen people pronounce this dibal. This is short for diisobutyl aluminum hydride. It's a less powerful reducing agent. And so we can actually stop the reduction of the ester at the aldehyde. So it's a useful alternative to the lithium aluminum hydride if our goal is to make the aldehyde as opposed to the primary alcohol. And one more reaction, but again, this is analogous to reactions that we've already seen for the acid chlorides. We can react esters with Grignard reagents to form tertiary alcohols. And so we get rid of the Z group, and we add two R groups, based on whatever the identity of the Grignard reagent is. And so this mechanism is exactly analogous to the reaction and the mechanism for the reactions that we saw when acid halides reacted with Grignard reagents. And the mechanism is also very, very similar to the reaction of these esters with lithium aluminum hydride in their reduction. And so for the final slide, if we take a look at that mechanism, just like the mechanism we saw before with the reduction, we start with a nucleophilic attack. Now, instead of hydride being our nucleophile, we have the alkyl anion from the Grignard reagent. We then have the loss of leaving group and the reformation of the carbonyl bond. We then have another attack of the nucleophile from the Grignard reagent. We're left with this charged alkoxy ion, and so the final step is we separately add water, right? Because we added water to the Grignard reagent, it would destroy it. So after the reaction with the Grignard reagent, we add a proton source to give us the neutral product.